So last time we defined what a tree is, and we gave some examples, and we talked about some tree terminology. Now, we're going to talk about some properties of rooted trees, and one of them will actually apply to all trees. But I just need to lay out some notation that we're going to use. So we're going to let M be the number of edges. So these are, remember, these edges are the connections from two nodes that tell me the parent-child relation for our rooted trees. It's just a connection between two nodes, okay? So just keep that in mind. And N be the number of nodes. Also, we're going to let what I'm going to denote as number internal be its, meaning it's as in the tree's number of internal nodes. So remember, an internal node is a node with at least one child. And number of leaves be the number of leaf nodes or leaves. So recall that these are the nodes that have no children, right? So it's worth also noting, just for you, because sometimes it's actually quite important for us to use this fact, is that the number of nodes comprised of the sum of the number of internal nodes plus the number of leaf nodes, right? Because there's only two kinds of nodes, leaf nodes and internal nodes. So we're going to prove our first theorem. So I'm pretty excited about this. We're going to start nice and easy. So for any rooted tree T with height h, it has to be, so what we're going to prove is that the height, remember the height is the maximum depth of a node, is always going to serve as a lower bound on the number of internal nodes. So that the height is less than or equal to the number of internal nodes. So we're going to prove this claim. Now this looks like something that'd be like, oh, well, do I have to like do some crazy thing? Like, what I'm going to be showing you here is that we can use some very basic counting arguments to establish this. So before we get kind of thinking about this too hard, we need to kind of have a game plan. I always like to talk about a game plan. So first, remember, this isn't about just one example of a tree. It has to be true for any rooted tree. Any rooted tree. So we start off with that. So consider any rooted tree T of height h. So we're going to consider any such tree that, as we've listed out here. Now, I'm going to do a little bit of a doodle to help us understand what this tree might look like, okay? But give me a moment. I just want to show you something that we can use from the definition of height of a tree. And this will help guide us to what we might want to look at. As T has height h, remember the height is about the tree. As T has height h, I'm sort of squeezing it in there. So if it has height h, by definition, there is a leaf node, right? At level h of t. So recall that we had these different levels of the tree. We had level 0, level 1, level 2, and we go all the way down to the depth for which it would be the maximum size, right? And that number is the height. So please keep that in mind. So let me just doodle a picture of what that might look like. So let's doodle a little picture. I'm just going to do it over here so you can kind of see what I'm talking about here. So we got some nodes here. We got some nodes over here. This is the root node, right? That's the root node. This is the root node. So this is at level 0, level 1, right? So remember that we draw our trees downward from the root. And you're going to see that this is actually kind of helpful for us to visualize this in our heads. So just keep that in mind. So it might be the case that there's something else going on over here with what we would call this subtree, rooted at whatever this is. It may have no node there. I'm just saying there's some subtree there. It might be empty. There might be some stuff there. Now, let's make that a little bit shorter. There might be some stuff here. I don't know. The point I'm getting at is that this tree has height h. So when I look at this level of the tree, this node will be on level h minus 1, and this node will be on level h. So that's very important for us to observe, okay? Does everybody see that? That there has to be a leaf node, because remember, that's a node with maximum depth in our example of this diagram. It's just a diagram of a rooted tree. So that node is very special. There could be many of these nodes in this tree, but we just need one of them. And that follows from the definition of T. So because T has height h, that means that there has to be a node at level h of the tree. So now we're going to give that node over there a name. We're going to call it V. And I want you to look carefully at what we could say about V, because V is a very special node for how we're going to argue this. So the game plan I have is we're going to look at this node V. We're going to then ask, okay, if we have node V, what can we say about the internal nodes in relation to V? If we can say something nice about that, then we're done, right? That's it. That's it. So let's. Okay, so we called. Let's give that a name. Let's go. There is a leaf node, V. So node V is a leaf. So observe that all the ancestors of V, what can you say about all the nodes that are ancestors? Most certainly you think of this like a family tree, for example, you would agree with me that the root would be the furthest most ancestor back, right? But you could say if I looked at V, say this is me, right? Well, I didn't just sprout out of nothing, right? Some people like to think that, but but in reality, no, I didn't sprout out of nothing. I had a parent, at least one parent, right? So notice that I have a parent, but that parent also had to have a parent because they can just poof into existence. We're only allowed to have one node that's allowed to do that, right? Which node is it? Which node is it? It's the root. The root is the only one that's allowed in our definition of a tree to poof into existence like that. So we now could say something very nice about all of the ancestors of that leaf node. That all the ancestors of V are internal. They're all internal nodes. They're all internal. And where do they occur in terms of levels of this tree? Where do they occur? And occur at levels 0, 1, and so on until h minus 1, right? There's this one, right? Its ancestor, then that's ancestor, and so on until I get to this ancestor, and then there's this ancestor, the furthest most ancestor, the root. So how many levels are there here? Well, I want you just to ignore this bottommost level. How many levels are there? How many levels are there, everybody? Well, it's 0, 1, 2, 3, all the way up to h minus 1. So meaning it's h minus 1 plus the 0th level, or aka the first level. It's kind of confusing language, but keep in mind that level 0 is a level. So it's one higher than h minus 1, making it h. Totaling to h internal nodes. So if you can argue that there's at least h internal nodes, there it is. That's the claim, right? That's the claim, right? Then we're done. Therefore, so now we got to conclude our proof. Therefore, there are at least h internal nodes in T. Neat, right? So in this proof, all we did was we looked carefully at what's special about a leaf node, namely that every ancestor it has must be an internal node. Then we counted how many there could be along this pathway of ancestries up to the root, and we realized that there has to be h of them because mine occurred on. So I looked at a leaf node, which had maximum depth. That is the one for which the height will be determined to be h. And I just counted them. That's it. That's all I did. Neat, right? So let's prove another property. So next, what we're going to do is we're going to prove a property that's true for any tree, not just rooted trees. But you're going to find that thinking about it as a rooted tree helps us think about how we could prove this claim. So here's the theorem. Is that the number for any tree, it has to be that the number of edges is always going to be equal to n minus 1, where n is the number of nodes. So this is the number of nodes. And this is the number of edges. So it always has to be that the number of edges is one less than the number of nodes. So let's think about this. Now, again, I'm going to employ another counting argument. So this one is going to be kind of nice because I want you to think about this. Okay. I would like, and the technical phrase for this is called a combinatorial argument. I'm going to have two sets of things I want to count. I'm going to try pairing them. And the idea is if one of the sets is bigger than the other set, it has to be that one object in one of the sets has to not be able to be paired with any element of the other set. So that's what we're going to be doing under the hood in this argument. It's called a combinatorial argument. I would like to know by how much that mismatch occurs, if it does occur. So we're going to find a way to pair vertices and edges in this tree so that I can I can determine if there's some mismatch of counting or pairing them, and determine by how much. So what I'm going to do is I'm going to make a fun picture for us. And remember, the picture is not a proof. It's just to help us understand what we're up to here, okay? Because I would like to give us a game plan for what we're talking about. Okay, so here's an example of a rooted tree. But keep in mind, this argument applies just the same if we take any tree, assign a root, and then we dictate parent-child relations over that tree. So now what we got here is we got ourselves this rooted tree. I would like to find some way I can carefully count the edges and vertices by trying to pair them. So there's something really neat about the root node. The root node is very special because of something that we've discussed in the past, is that the root node has no parent. But what can you say about all the other vertices or nodes? These nodes, all of them have exactly one what? They always have exactly one parent, right? They have exactly one parent. So what can you say about that then? Well, every one of these nodes, in fact, these two as well, they all have parents. Likewise, what does that dictate? There has to exist an edge between the two nodes, namely the parent and the child. So that means that there's an edge for each child. So here's an idea. Why don't we try doing something like that? So why don't we I'm going to take my blue marker out. Why don't we try to pair each of these edges with the child that comes from the node that edge is connected to, like this. So notice that this edge can be paired with that node, because notice that there's only one parent for that node, right? There's also one parent for this node, but there's an edge that connects them, right? There's the parent-child relationship I'm taking advantage of. So let's see what happens now when I try pairing them like this. And I would say that this proof is really nice and simple. This is something I love getting students to just think about. So pair every node with the edge connecting it to its parent. Remember, every node that we've circled or put an oval around here, you can have this guy, every one of these guys connects distinctly to one parent. Oh, thank you. We have ourselves a lot of fun here. So let's see here. We have the connecting to its parent, right? So this is how I'm going to pair nodes with edges, right? That's how we've decided on. But what's special about this? Okay, so notice that. Now I'm going to take another marker just for dramatic purposes. Okay, this edge is paired. This red marker has decided it wants to go caca. It's going to go bye-bye. Woo! It's gone. It's gone. You heard the thud, right? So let's use blue then. Okay, so this node is paired with this edge, right? This node is paired with this edge. 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 How did we define how we paired them? We looked at the edge that connects our child to the parent, right? That's what we did. Oh, thank you. I'm looking forward to hearing from you. So let's but there's one I didn't put an X there. Which one was it? It was a very special node, right? It's this one right here. The root. The root was not matched. But that's exactly one node that hasn't been matched. One node will not be paired. The root. Right? It's a very special node because it has no parent. Therefore, there is one less edge than nodes. You know, I forgot to indicate the end of the proof on the other one too. Let's do that. There we go. So make sure we have to indicate the end of our proof with a little box. But no, so now we have, so by using a very simple combinatorial argument, by counting these nodes and edges, by finding a way to pair them, I found that there is a special one that never has a parent, for which it cannot be paired by any edge by using this technique. And that means that there has to be more nodes than edges, and we've determined there's exactly one of them. Hence, this result.